Hi. So I want to finish going through intrinsic viscosity. There's a few more things, I guess, to say about it, and then talk about dynamic light scattering. Both measure the hydrodynamic radius. So that's kind of where we are here. Let's see. Yeah, this is okay. Somehow the computer was acting funny there. It's probably operator error. Move this up. Wait, so we know that, let's see, why did that happen? There. This guy, sorry about that. Up there. So, so we know that the hydrodynamic radius is different than rates of gyration. So we talked about that already. Basically, if this is a sphere, for a sphere, this hydrodynamic radius is going to equal the radius of a sphere. So it's a radius of an equivalent sphere put into motion, like with kT energy moving, and then fusion coefficient is going to equal kT over the friction factor for the object, and then the friction factor from Stokes' law is 6 pi times the radius of a sphere, and then the viscosity of the solvent. So this is for the hydrodynamic radius. So this is the hydrodynamic radius. So radius of an equivalent sphere to whatever diffusion coefficient you happen to measure. And so basically for a sphere, the radius of gyration squared is 3/5 of the 3/5 of the radius for the sphere squared. Right, so radius of gyration is less for a solid object. So you can see here, when the coil collapses, the radius of gyration is less than this is going to be square root of 3/5 of the whatever the radius of the sphere would be if it was a solid object. Then when it becomes a fractal object, the radius of gyration is larger than the equivalent sphere radius. And that this number, the RH, is going to depend on how well draining the chain is. So you have some structure. So you're going to draw an equivalent sphere, and you have to consider the solvent molecules around that. Like, do they totally stick to it and make a real sphere? Do they drain off, and then your hydrodynamic radius is just the size of the diameter? So it can vary depending on how that works. Kirkwood worked out a mathematical way to calculate the hydrodynamic radius of a polymer or any object, actually, if it's non-draining. So this equation's for non-draining, meaning this condition, like the total size of the object. So this RH can be calculated under the assumption of non-draining. Under the assumption of draining, it depends on the extent of draining. So then this becomes more difficult to calculate, right? But you can see that this is kind of a different than the radius of gyration calculation. We did this double sum, so it's direct of the second moment. Right? So the end-to-end distance is the second moment of the distance separation of all the parts. So it's this thing squared, and this thing is like the inverse of the first moment. So that the RH is going to represent a different moment of the distribution of sizes, and the radius of gyration is going to have a different value because it's calculated with this kind of inverse law. So this kind of inverse summation is called a let's see, the kinds of means are numerical means, geometric means. Geometric means you have x1, x2 square root to get the geometric mean. And this one is called the numerical is also the arithmetic mean, arithmetic mean, or numerical mean. And then geometric mean is that, and this is another kind of mean where you sum the inverses, which I don't remember the name of it. I'll dig it up somewhere, but anyway, this kind of mean has a weird thing that, so say this is the kind of mean you would have, say you want to drive to Columbus, and you're going to drive halfway at 100 miles an hour and then the other halfway at 10, right? So the average of that would give you something like 55. That would be the numerical mean. The geometric mean would be the square root of 1,000, right? Which is like 330 or something, 30 or 40, like 32. Right. So numerical mean's bigger than this geometric mean. Then this kind of mean is going to be a weird thing. Like 1 over 100 is small, so it's 0.1. There's 0.01, and then you're going to add in 0.1. So the only thing that matters with this inverse sum is the small one, right? You add in that, so you get 0.11. And then divide that by 2. So you take the inverse of that and you're going to get something like 5 or something bigger than 10. So it'll be like 15. Right. So it's weighting these small things. This kind of inverse sum weights the small things bigger than the little things, because 1 over something small is something big. So the small things are weighted heavier, whereas this thing is going to weight, the square is going to weight the heavy things more, because squaring 100 gives you 10,000, squaring 10 gives you 100. Right, so 10,000, 100 is meaningless to 10,000, so this basically becomes the largest number. This basically becomes the smallest number. So you're going to get, if there's a distribution, you're going to get different values for these things. And also, so it reflects also in the structure. So you can say, like, because it's an inverse sum, it's going to give you a smaller number than RG if it isn't just a straightforward calculation like it is the radius. When it's a sphere, it is the radius, so there's no calculation involved. So the Kirkwood equation gives you some feel for how these two numbers change for a fractal object, right? And it kind of indicates that RG would be larger than RH. So that's kind of one thing to look at here. So using this to quantify structure is a little bit dicey, with these fractal things. But I'll show you that people have done that nonetheless, right? Especially comparing these two numbers. Comparing the two numbers, you can get a feel for what the makeup of the structure is. At least they've inferred that you can. So people do that. And we already, so it's important in dealing with intrinsic viscosity to remember, like, there's 4 different viscosities that people talk about. Right, so it isn't clearly defined, like, what these are. So the relative viscosity is viscosity by the solvent. Right, so that's a unitless number, but it reflects the scaling. It's proportional to the viscosity. Right, so when the relative viscosity reaches 2, that's where you generally get entanglements. That's where you start to see the takeoff. If you plot the reduced viscosity, you'll see, like, N reduced by C plotted against concentration, and then or you just see the reduced, or you'll see the specific viscosity plotted. So that's the same thing as the specific. And so that's the let's see, reduced is the specific. This is the specific by C. Sorry, this is the reduced. That's what I mean by this thing gets confusing. So specific is viscosity minus solvent over solvent, just same thing as the relative viscosity minus 1, because this thing is relative viscosity and this would be 1. Right. So, and if you divide that thing by C, then you get the reduced viscosity. Right, so this thing equals the specific viscosity. If you divide by C, you get the reduced viscosity, which has units of inverse concentration, just like the intrinsic viscosity. So intrinsic viscosity, you have the solvent viscosity times 1 plus the intrinsic times concentration. So if you take, so you're going to naturally produce the relative viscosity is viscosity over the solvent times 1 plus intrinsic times C. And then the equals that. And then if you take this minus 1, so if you take n relative minus 1, sorry, that's going to be the intrinsic by C. Right, so if I divide by C, I should get the intrinsic. So if I plot that's the same thing as the specific, just to confuse things. So if you plot this, that's not the specific. That's specific by C, which is the reduced. Right, so we have relative, specific, reduced. And they all are kind of tied into this intrinsic. So you got to plot reduced versus concentration, and it should go to 0. And then it should have a slope. The slope should be this intrinsic viscosity. Right, and again, what the intrinsic is how much adding the stuff to the material kind of displaces the fluid. So as you add, so if you have the fluid, and if it's spheres or solid objects, it just fills up the space. And then because it's displaced that fluid, the viscosity increases. The apparent viscosity increases because you've removed fluid and you've replaced it with bricks. Bricks don't flow. So basically the viscosity appears to increase because you've added bricks to it. Right, so the bricks could be at the bottom or they could be floating around. It doesn't matter. As long as it kind of, as long as they displace the same amount of fluid. So this is just a displacement law. Right, so the question is, what's displaced? So if you have a brick, so it displaces the volume of the brick. That's pretty simple, right? So it's a fixed number. It doesn't matter how big the brick is. The amount of brick that you put in, it'll displace the amount proportional to the C. So this intrinsic is a fixed number. For spheres, it's 2.5, and Einstein got that number. For polymers, though, this becomes more confusing because the density of the polymer, so it's got a high density when it's a monomer, and the density drops as it becomes a polymer. And the bigger the polymer, the lower the density. So the density drops with size or molecular weight for polymers. Right? The density is the mass per volume, and then the volume is the size cubed, and the size goes with the mass to the 1 by df. So you're going to get that the density is the mass to the 1 minus 3 by df by the fractal dimension. So the fractal dimension effectively just gives you the density. Fractal dimension doesn't tell you anything about what the thing is, it just tells you its density. All right, so if you want to know, you say like people will make correlations with fractal dimension, like you have a linear chain in a theta solvent, it's got a fractal dimension of 2. And then if you branch that chain randomly, it's got a fractal dimension of 2.5. Right, or we saw that if we took a sheet of graphene and then we let it form a self-avoiding walk so it crumples, it goes from a dimension df of 2 to a dimension df of also 2.5. So you can see that a crumpled graphene sheet and a randomly branched polymer aren't the same thing, right? But they have the same fractal dimension. The thing that's the same about them is the density is the same. If you spin these things around in space, they have the same mass density. So the fractal dimension just tells you the density. It doesn't tell you anything about what the thing is. But you can kind of infer that if you know it's linear chains and then you know the dimension went up, you know it becomes branched. So you can kind of infer that. But you can't say distinguish that thing from a crumpled sheet. Right. That becomes a problem in things like proteins, where a misfolded protein will make sheets. So you make amyloid fibers, which are composed of beta sheets. So the natural way for proteins to misfold is to make sheets, which are dimension 2. And then an unfolded protein in a theta solvent is also dimension 2. So if you do scattering and see dimension 2, you could either say, oh, I have a Gaussian chain, or oh, I have a beta sheet. And two people could kind of argue about that for a long time. Right? Like what exactly is it? So it depends on your framework of looking at it, what it is. And it has, actually, you can't tell, it's just telling you the density. So the density doesn't tell you what it is. Anyway, so then this intrinsic viscosity is going to have the same thing as the inverse of the density. So it's going to be molecular weight times 3WDF minus 1. So then you can make the table that if you have DF of 1, then this thing is 2, right? The Markov coefficient, so intrinsic is K times M to the A. So this is a rod. If it's 2, it could be a sheet or a theta coil. And for 2, it's going to be 0.5. And then you could have expanded coil. DF is 5/3 or 1.7, depending on how you want to look at it. So then this thing would be 0.8 or what does it become? Let's see. Then DF is let's see. So then it becomes 0.765. Right, so that's kind of the actual number, and this is an approximate number from the Flory-Krigbaum. Like when you do the Flory-Krigbaum and use an approximation, you get 5/3. If you do a numerical integration, you get 1.7. And then you get these other. So these are actually the numbers that probably you should use, but these are easier to remember. Right. So, right, so that's kind of how this intrinsic viscosity is generally going to behave. And then we saw that like a good solvent sheet also has 2.5. So it's also let's see. Oh, good solvent theta sheet has a dimension of 2.5, and then this thing becomes 0.3 something, I think. Right, 3 by 2.5 is let's see. It's 0.2, I guess. This becomes 0.2 for a good solvent sheet. And then also for a randomly branched theta chain has the same dimension as a good solvent sheet. So 2.5 and 0.2. And you could do different objects. And if it's 3D, then 3 by 3 is 1 minus 1 0. So this A number is 0, and it doesn't depend on molecular weight. End of the 0 is 1, so you just have a fixed value. Then that K is 2.5 for a sphere. Right, so this thing, you can kind of map out what you can get. This is basically looking at density. This is just a density map, and that's all you can get from this Markov thing. I mean, so you have to add in the complications of what the draining is of this. This is all for a non-draining. All this case is non-draining. So if it's draining, then this whole thing becomes muddled, right? So it depends on how the solvent drains from the chain. All these numbers will change. So basically, you get some number for A in a given solvent at a different temperature, and then you can map out the molecular weight just using this capillary viscometer. So it's a little complicated for something that's absolutely the simplest thing. There's an old saying that the simpler the experiment, the more difficult the analysis. This is kind of an example of that. You just get one number out of this. Interpreting that number involves some kind of mental gymnastics. So this is the kind of thing you look at, you might see floating around the literature, although it's kind of rare now to see this. This was something more from maybe the 1960s and 80s. People were looking at different shape objects and came up with these different approaches to talk about this. This is a power series. It starts to look like we had things like the exponential of x equals 1 plus x squared by 2 plus x cubed by 3 factorial plus x4 by 4 factorial. So you can start to say, well, if I have any power series like that, I could say it's an exponential. So if I have this thing, then I could say, well, I'm going to take a log of this. I'm going to take a log of n by n naught, because I could say this is an expansion of power series like the exponential. So you take if you have this thing, you take log of this thing, which is the viscosity divided by, so it's a relative viscosity, n by n0, and x here is x is the concentration times intrinsic, right? So then you can just say, well, I should do ln of viscosity or viscosity 0, and that's going to equal the argument. So if I take that by concentration, that should be a pretty good function to describe the entire power series instead of just the one. So this assumes that you have a prefactor, like a fixed prefactor here, but actually that prefactor changes, like K1, K2, whatever, depending on the kind of interactions you have in the fluid. Right, so the first one is for isolated colloidal objects floating around. And then this is for binary interactions. This is just like a Taylor series expansion, like a viral expansion, where we expanded the osmotic pressure, right, as a function of concentration. And the second viral coefficient. So first is the first viral coefficient, which is like one of them, molecular weight. And this is the second viral, which is 1/2 minus chi. This is the third viral, which is that C that we use for the collapse, right? But this isn't a thermodynamic thing like pressure. This is a kinetic thing, right? So there's a similarity. It's kind of an odd similarity because the idea is exactly the same though. Unary, binary, ternary, etc. interactions. So one isolated dilute, ideal. This is binary, like the first order, non-ideal. This is 3 interacting. Right? So basically, there's a similarity between this and the viral expansion, but it's limited how far you can push that, because this is not a thermodynamic thing that you're measuring as a kinetic thing. So you're looking at flow, right? So it's not equilibrium because it's flowing, right? So this is kind of steady state. So there's a difference between equilibrium and steady state. These aren't going to be dependent on temperature. Like it's not going to be thermally dispersed. It's kind of a kinetic dispersion going on. So there's differences but similarities. The concept of this expansion is similar to the viral expansion for osmotic pressure, but the actual implementation is quite a bit different, right? So you have to be pretty careful how you compare these two equations. Thermodynamics and kinetics aren't the same thing, in other words. Anyway, so here's the Martin equation, is this exponential, right? So this kind of exponential term comes out of this, just a comparison between this expansion, this kind of expansion for exponential, and this. So that's assuming that all of these k's are the same number. So that's one approach people use. So you'll see this will be a plot of Where's Martin? Here, so it'll be a plot of the specific log of the specific viscosity versus concentration, because of this Martin constant times the intrinsic. Right, and then you can determine that from the slope and the intercept. So there's a bunch of these equations. So there's a Kramer equation, which is also a log based, kind of based on the same thing, right? And then Martin equation, I mean, it's written in terms of exponential, but it's basically similar to the Kramer equation. And then the Huygens equation is just a straight, use this equation for instead of using it to 2 terms, use it to 3 terms. And then you get another parameter out of it. That parameter will reflect the interactions between the polymer chains, right? So in the context of a flow experiment. So it's not the thermodynamic interaction like 1/2 minus chi, although it's related to that. It's the interaction under a certain shear rate. So this number could change with shear rate. In other words, how fast you pump the fluid through will change that number. Let's see. So anyway, these are just plots of how this thing behaves. So this would be normally, you expect this to be linear and intercept at 0, and the slope would be the intrinsic viscosity, right? So it doesn't intercept at 0 unless you're at low molecular weight. The slope changes with molecular weight, so the intrinsic viscosity increases, so the density decreases. Right? So intrinsic viscosity is 1 over the density. So the steeper the slope, the lower the density, and you expect the density to drop with molecular weight, and that's what happens. So as the slope gets steeper, it's a less dense object, and the higher molecular weight ones have less density. And then you reach a point where it falls apart, right? And there's a dashed line that's being fit with one of these functions, right? So the straight line is just the intrinsic, just the second order. Then this curvature would be like the 3rd order, or you're using one of these other functions like the Martin equation or the Kramer equation to get some kind of information about how the things interact within a shear field. Right? So what's the interaction within a shear field, and whatever mystical information you want to get from that, you could get it. You could compare different solvents and say what the interactions are, things like that. So anyway, we aren't that interested in this stuff. This is a mapping that shows, so there's different books on this. One is from the Simha, the guy from Case Western, who this was his, well, I don't see his book here. I don't have any of these books. Oh, Jameson, right? Jameson wrote a book. Jameson's also at Case. Jameson kind of worked with Simha, was the guy who came up with a lot of things about different colloidal shapes and how they impact the intrinsic viscosity. Jameson did some other stuff, like he does dynamic light scattering and also positron annihilation, which is a way to measure free volume for glass transition. So he was kind of 3 fields he worked in that I know of. But anyway, there's this other book by Clausen and Kulik, right? Most of these people have some relationship to Simha from Case, this intrinsic viscosity business. Anyway, so this is just looking across also different molecular weights and showing this point where there's that divergence. You can figure out what C star is. Right, so again, this is C star in the context of a shear experiment. So C star in this context might change with the rate of shear that you put through. Right, but there's a cutoff point where these equations won't work. So he's calculated C star, mapped out where that cutoff is, and said he's in good range with the measurements he did, and it's verified because it's linear there. Right. This is let's see. So these are all linear, right? These are all linear plots. So that the log term, you would do a log linear plot, like the Martin equation would be a different plot they'd use. This is just showing the same thing. Like, oh, this is showing like some molecular weight effects and then solvent effects. So put the same polymer in water. It's got a lower density. It's a steeper slope, lower density. Means water is a better solvent for this polyamic acid. then you put it in 4-amide, which is our that's our same thing as that DMF, except without the, it's DMF without the, so 4-amide is let's see, 2, 3. There's something else here. I guess there's an OH there. No, no, this isn't H, sorry. It's formaldehyde. So formaldehyde is that, and then you take off one of the H's and put an amide on. So that's 4-amide, right? And then if you put methyls here, that's DMF. And so this little ditty, you start with formaldehyde, and you stick on an amide, and you methylate it, and you get DMF, which is that's a nanotube solvent. And then this 4-amide is a relative of that. And then glycol is just OH. It's like an alcohol, but it's a double alcohol, right? So you have 1, 2, 3, 4. There's 2 hydrogens sticking off, and there's 2. That's glycol, right? So these are variables. So this is expanding the coil to different amounts. Glycol shows almost no change, right? So it's a poorer solvent than water. So it's poor, better, best for this polyamic acid. I think that's what PAAM is. Probably acrylamide. That's like acrylic, like a carboxyl sticking off, and then it's got an amide sticking on the other side. So it's a vinyl polymer, right? So that's water soluble. So you can see the solvation goodness you can see from this, but this isn't measuring the chi parameter, which is a measure of the this is just measuring the hydrodynamic size. And again, depending on how the water sticks in the coil, this hydrodynamic size can change, and definitely changing the solvent with something that hydrogen bonds is going to change the draining capacity of the chain. So you can see that taking this thing as like a thermodynamic number is a mistake. So you have to be really careful, because it's easy to interpret the intrinsic viscosity as a thermodynamic number, but it isn't, right? Because it's a dynamic number. So it's going to depend on the shear rate. It's going to depend on how well the water kind of sticks under that condition of the shear rate. That'll change the size and the density of the object, the apparent density. So the chains could all be the same size. It could just be draining differently when it goes to different solvents. So you don't know if it's more expanded coil. So if it was the same conditions, you'd say it's a more expanded coil. But basically, because the conditions change, which is the thing you're trying to see if it expands in, then you can't tell, because the draining would change. Right, so you have to, this is a tricky number to mess around with. So anytime you take kinetics and try to get structure or thermodynamics from it, you have to be really careful. It's almost not possible to do it, right? Morphology from rheology is theology, is the old expression, right? So you have to be pretty careful what you're doing. This is the same thing, molecular weight series. This is also a linear plot. Somewhere in here I have a Martin equation. This is just showing the business of dimensions. We already went through that. We already talked about this. This is the thermal effect on this. So what about temperature? So viscosity is an Arrhenius. It's kind of like it's the classic Arrhenius function. It was actually the Arrhenius function. This function was invented for viscosity. So this should be negative here. This is a barrier energy. So you have the concept of Arrhenius behavior, which is thermally activated. So Arrhenius is thermal activation. So you have an energy barrier. Something can happen, but it has to go through a barrier energy, and you have some reaction coordinate, which you don't know what it is. But in this case, this map and the idea that this is exponential minus E over KT know if I can change that. Yeah, this should be minus here. Is that an equation? No, it's a picture. That should be minus anyway. So that's an activation energy. It's that height of that barrier. Right. So viscosity is what this was invented for. This was invented for viscosity. So the model is that you have two spheres, and then you have a sphere of your stuff. In order for it to flow, it has to go over here. In order to get here, it has to push this guy there, that guy there, and that takes an activation energy, EA. Right? And these things at the same time, so superimposed on that model of flow, is thermal agitation, right? So thermally, these things are randomly moving with KT. Oops. So there's a balance between this EA and KT. So you have EA over KT is going to give you kind of the probability that this guy went there. So it's going to be exponential, gives you the probability of flow, which equals viscosity. Right, and then you need a constant here. That's the zero, eta zero, which is like temperature infinity. Or if the barrier energy was zero, then this would be one, and that would be eta zero. So if somehow you could remove this barrier, then it would still have a viscosity. It would be this zero viscosity. Then you get the viscosity from this. The thermal dependence is exponential. Right, so you can see that the viscosity drops exponentially with temperature. This is absolute temperature, right? So you have to do this in Kelvin. And you can easily verify this with anything. We do this, when I do teach a lab, we verify this with PDMS. It's pretty simple. For polymers, all right, so for polymers, when you flow, you start with this and you maybe go to this. So you straighten it out. So there's a change in entropy too. Right, this energy initially is just a delta H. Right, so you know this energy is actually, like, you could think of it as a free energy. It's going to have delta H minus T delta S. Right, so if you have E by KT, then you can say that you have exponential of delta H, so minus delta H plus T delta S over KT, right, which is going to equal exponential of some number like A, which is delta S, or just call it delta S by R, right? And then the delta H will still be there. So minus delta H over KT. This delta S would be like, how does the chain straighten out when it flows? Right? Because you're talking about the viscosity here. So the structure can change. Or maybe it had to do with water association with it. Could be a lot of different organizational things with this delta S. Right, so that gives you two parameters for viscosity temperature dependence. There's another twist to that called the Vogel temperature. So in a polymer, like you have a glass transition, it doesn't flow after that. Right? Or you could have some other temperature, like crystallization, where flow stops. So this absolute temperature that's based on zero is a zero number for flow. So when you reach temperature zero, the viscosity goes to infinity, right? Because this becomes infinity, exponential infinity is infinity. So it becomes infinity, right? So at zero temperature, you get infinity, it becomes a solid. But things can become a solid before 0 Kelvin. So you can say exponential minus EA over KT minus TV, the Vogel temperature. Right, so viscosity can have this other temperature. So then you can have three parameters you can dump into this thing if you want to fully describe T minus T Vogel, this zero temperature. So there's 1, 2, 3 numbers you need. And that will give you, you can rearrange that to be the Williams-Landau-Ferry WLF equation for viscosity. Also has three parameters. And you can explain those three parameters in terms of entropy, enthalpy and this Vogel temperature, which somehow should be glass transition. It isn't usually exactly the glass transition, but it's somehow like it. It's near it. It's near the glass transition. Since a glass transition is a kinetic phenomenon, it changes with the rate. So this Vogel temperature doesn't change with rate, even though it's dependent on viscosity, it's dependent on rate. So again, you're into like the never land of associating thermodynamics with kinetics. You know, and generally, like thermo equals kinetics, not equals, right? You can't take kinetics and say thermal, like the two are separate things. Basically, you can try to force fit it. And that actually, this will predict like anything, but for most polymers, it's just a simple thermal dependence, like in Arrhenius, that should be negative here. And that'll work fine as long as you're far from the glass transition. And again, near the glass transition, you have one parameter, the Vogel temperature. And then if you get, if you find out that doesn't work good enough for you, you can add another parameter, which is this entropy. And again, the entropy change probably changes with the shear rate. So that becomes, you have to really specify the shear rate for this thing to work. Right, but generally there's a WLF equation for polymers that people talk about, which I don't remember offhand, but I can find it in a second. Oops, that's the wrong place. Where, it's definitely on the web page somewhere. But so there's like 3 WLF parameters, and they can be back to this. Let's see. So these are guys from Williams, I think was British. Ferry was at Wisconsin, University of Wisconsin, and Landell, I think, worked with Ferry. So this is the 3 parameters. See the T reference? So that's a Vogel temperature, shifting the temperature scale to the glass transition, say. So you can use TG as the TR. He says that's erroneous, blah, blah, blah. Basically, the idea is that's TG or something like TG. And then these C1 and C2 are tabulated for different polymers. You can see them in the Polymer handbook, or you can look them up other ways. Just the WLF parameters will give you the shift factor, and that gives you the temperature dependence of the viscosity. So, so that's the temperature dependence of this thing. You should have already seen that. I guess we took intro to polymers, like temperature dependence of viscosity. And also just basically, if you took fluid flow, you should know that it's going to follow an Arrhenius behavior. This is the Simha stuff about different shaped colloids like prolate, oblate, ellipsoids. He gets this new parameter, which is the intrinsic basically. So these are for solid objects. So the new changes depend on what shape it is. For a sphere, 2.5, and then he gets different numbers for different kind of objects. So is that business? So we don't really need to dwell on that. Then there's this is showing shear rate dependence. So you're always assuming that you're in the plateau shear rate. So the Newtonian plateau region. So as you increase shear rate, then you see shear thinning. This is log plot, so it's a power law dependence. So you want to be in the part where it's not changing to do these measurements. And if you have a capillary flow, which you're using the capillary viscometer, this variable shear rates across the gap. So the middle has 0 shear rate because it's flat. In other words, the slope of this velocity profile is the shear rate. So basically in the middle it's 0 shear rate, and at the edge it's pretty high shear rate because you have no slip at the wall. So the shear rate is a gradient in this thing. So this, like where you are in this plot, varies depending on where you are in the radius of the capillary. Right, so this capillary viscometry isn't, unless you're going at very slow flow, for shear thinning fluids is not an optimal technique to use, but it's simple to do. So people just do that, and they assume that all the mismatched things kind of get washed out because you're just measuring the time and you divide by the solvent time. So the business of branching for this thing is important too. Actually worked up a bunch of stuff on dynamic light scattering. It looks like it's probably not going to make it here today. This is what happens if you take a polymer of similar molecular weight and measure the intrinsic viscosity as a function of molecular weight. So there's a linear chain, and then low density polyethylene is kind of a shotgun thing. So high density is basically kind of linear. I mean, high density has these long chain branches in it, so it's not exactly linear. But low density, which is the original free radical polyethylene, has this tree structure to it. So it's got a lot of branches. So it's arboreal. Call that arboreal. It's an arboreal polymer. Depending on how bad things are, it can be more and more arboreal, right? So this is going to have some pretty strange flow properties, different than a linear chain, right? So we had the Mark-Hoang coefficient. So there should be, like, the intrinsic should go. So if you plot log.
Dr. Beaucage,
Yep.
we can't
Sorry.
see the screen
Thanks.
right now.
Sorry. So if you plot log of the viscosity versus log, so you're going to have log of K plus log of M, and then A is a prefactor. So that's a straight line with slope of A. Okay, so you expect to see intrinsic versus molecular weight, and it's a log-log plot. That should be a straight line. The slope should be A. But when you start looking at these low densities, that doesn't work, right? And then the dendrimer, I think we already talked about, it's kind of the super arboreal. So dendrimer, say you have a rule of 3, then every time you have another monomer, you do 3, and it could be other rules. So it could be 4 or 5. So this could be, so this is generation 1, that's generation 2, right? So this dendrimer is going to be this monster molecule, right? And that's generation 3, G2, G3. So this thing, even worse, right? So as you increase the molecular weight, you're basically increasing the generations. The thing swoops over, right? So the higher the intrinsic, the denser the higher the intrinsic, the less dense the let's see. The higher the intrinsic for a given molecular weight, expect it to go up with molecular weight. I can talk about density with this thing. I guess you can't exactly. The intrinsic itself is 1 over the density. So the higher it is, the lower the density. That's what it is. So the higher values are lower density. So as you're going here, you have the density that is decreases. So intrinsic increases, density decreases. Then all of a sudden, density increases as you go to higher molecular weight. So it's becoming solid. Right? It's becoming more solid. The limit of this density increases, it becomes solid, and this density becomes fixed. It becomes flat line. So basically, if this intrinsic is flat line, that's a solid. The reason it goes down is because who knows why. Basically, it's becoming more and more solid if this thing's curved. So it means that this, as you go to higher generations of this thing, then somehow this thing's becoming more and more like a solid object, right? So anyway, so you can get information out of this. Again, that's again getting morphology from rheology is theology. So you have to be careful. Like anytime you see kinetics used to describe structure, there's other things that are going on here. Like the solubility of the chain drops also. Right? In other words, in molecular weight, you can go from a chain that's solubilized, because we remember that when we plotted the phase diagram, so we have temperature and composition, and there's a line that goes up to the theta temperature. So as you increase molecular weight, so say you're at a temperature here, this one, the low molecular weight one, and the low molecular weight one would be soluble, and the high molecular weight is insoluble. Right? So there's also a solubility issue. As you go across molecular weight, the solubility drops, and it could become insoluble and precipitate out. Right? So there's a lot of things that could be. I mean, they're trying to get rid of that because they put the same material here that shows that it didn't precipitate out. But who knows what happens when it branches, right? So basically, it's difficult to do. You have to criticize when you see that they're doing kinetics and they're trying to measure structure. But you have to be critical of that. You have to be really careful because there's a lot of things that can affect kinetics. It's not just the structure. So it's not like you're taking a photograph of the structure this way. It's not scattering and it's not microscopy. So anyway, but nonetheless, you can get some information from this. The branching thing is particularly interesting because if you have a high density polyethylene and you have one branch for 10,000 carbons, so you have a linear one and you have one branch for 10,000 carbons. Viscosity, the melt viscosity, so zero shear rate melt viscosity is 35 times. And this kind of one branch for 10,000 carbons can happen in an extruder when you heat it up because you have these hydrogens inside of polyethylene can be abstracted, making a free radical. And if two chains like that meet, then you get one long chain branch just by putting the pellets in an extruder or just by taking your reactor powder and pelletizing it. So you make pellets that are going to be shipped by train to someplace. They're going to be put in another extruder. Then you make a part. Right, so it's 2 times it's heated up. Both times you can introduce these long chain branching. The viscosity can go through the roof for that. So basically, people in the polyethylene industry want to know about this branching issue. So it's an important topic. So one way to get it is from intrinsic viscosity. You can see there's a difference, right? So you take you can measure this G ratio, which is the race gyration of the chain, and they've loosely affiliated race gyration with hydrodynamic radius. And then you can work out functions for this G ratio, which is a branch divided by the linear. So B is branch, L is linear, they're the same molecular weight. It's RG, race of gyration, but they just swap in hydrodynamic radius for this, or intrinsic viscosity. And they just call it G intrinsic, right? And then from that G ratio, you can calculate F as the number of branches. Right, so there's some confidence in this because they correlate this with NMR measurement to get the branch content. So this G ratio is a big deal in the polyolefin industry, to use intrinsic viscosity to measure the G ratio and then get this. There's other ways to get the G ratio. I think that's kind of where we are here. Let's see. Linear branched, polyelectrolytes. There's actually more to this. This is an unending subject area. So yeah, the polyelectrolytes is a whole nother beast. So with polyelectrolytes, you have this issue. So polyelectrolytes, as you increase the number, the concentration, so C goes up, your counterion concentration goes up too. So say it was as a polyanion with sodium counterions. So as you increase the concentration of polymer, you increase the sodium content, which means the Debye screen length goes down, right? So you get, as you increase concentration of counterions, your screen length drops, and then they become linear chains. So you can go from a linear chain, like a polyelectrolyte isolated would probably be fully extended. So you have DF1, and then as you increase the concentration of the chains, DF can go to 5/3. And then you increase more, it can go to 2, right? Without any change in temperature. So this is expanded coil and theta. Right, so you can go through that transition, so it becomes denser. So density goes up, so intrinsic goes down. Right, so you can kind of see that happening here. This is a log scale linear. So this is basically like a Martin plot, right? So basically, so as you increase the concentration, you screen the charges, and then the density increases, the intrinsic viscosity drops, right? And the peak is maybe the isoelectric point, something where you perfectly match out the charges or something on the thing. So polyelectrolytes can have really complicated viscosity behavior, because of this screening effect. Also because they're linear to begin with, so they go through these transitions. You can see, like in a salt solution, this chain behaves perfectly well, like a normal polymer, right? You can get the density from the density from the slope, and then when you put it in water without salt, then you see this weird behavior going on. So something's going on with the charge, this charge screening thing's going on. This is from Colby, right? The guy that wrote the polymer physics book that's on the webpage. This was in the quiz, right? So basically this is for polyelectrolytes. This shows you can have, once you get to the C double star, you screen the charges, it becomes the linear chain. And then you can have an overlap concentration before that, and then you can have entanglement concentration, and it's separated by this weak slope part. And then once you get entanglements, it shoots up. And once you get neutralization, something else happens. So there's these various transitions that Colby can predict, and he demonstrates it with this plate 2 vinyl pyridine, which he can put salt in and then make it into a linear chain, make it into a non-polyelectrolyte. So he did that in another paper. This is the non-charged PV polyvinyl pyridine, and then charged without salt, without the Debye screening. This is this other curve, the blue one. So you can get a transition between a linear chain and polyelectrolyte to try to show that this transition regime between the overlap concentration and the entanglement concentration has different slopes for the two polymers. And that once you get this total screening, the two things are the same, because the red ones already with salt added, the blue one with salt comes from the counter ions for the chain. Then they match at the high concentration. So this is a pretty nice paper, 2010, where he kind of demonstrates this stuff more or less for the first time. So why don't we quit there? Sorry I went over, but hopefully we can just bury intrinsic viscosity though with this and then move on. I'd like to get to dynamic light scattering. Any questions on anything? So next week is the ACS meeting. I wanted to go to it. It's virtual, so I'm probably going to pre-record the classes next week, if that's okay, and then do it like I did for the APS meeting, if everyone's okay with that. But so if there's any questions, let me know. That's about it for today. No, I'll put out a quiz on Friday, same as usual, and then kind of go from there.
Are you accepting critical reviews this semester to replace
I don't
quiz
think you
grades?
need it. Like, do you need it for your grade, or let me see? I can look at your grade if.
No, I think it's fine. I just submitted one.
Yeah, it wasn't
before.
the grade. It wasn't going to help your grade. I looked at
Okay.
it. It wasn't exactly what I wanted. Usually we'd go through a paper, like you'd find a paper and then come to me with it, and then we'd talk about it. And then I tell you, like usually you go, it has to be on the subject in the class, something that we've covered. And then you have to bring a few papers, and I find one for you that's a good one that you could reject. The idea of is to reject it based on what's in the class. We've gone over in the class. So I think you didn't do that. It was something different than that. Oh, it was on like nanotubes or something. I looked at it.
Yeah, it was on a CNT PLA matrix. Okay, I just wasn't sure.
It was
Thank
something
you.
different. It was like mechanics or something, right? So it's just kind of different. Anyway, I graded it, but I don't know how to post the grade either on the Canvas. It doesn't fit in,
Yeah, no, it's no problem. I just wasn't sure if I'd sent it out.
I do have it, and I did
perfect.
grade it. I didn't send it back to you though, I think, but it wasn't the right thing. It was like, basically we'd have to find a bunch of papers. I don't think you need it. Like,
I think it's fine.
like you're undergrad, right? And
I'm in the graduate.
are you grad for chemical?
Yes.
Yeah, you guys will do fine. I mean, it'll probably, I'm not anticipating anyone's going to get a B. I don't know.
Yeah, I just wanted to make sure that that you had gotten it, so.
Yeah, I got it.
small
I
thing.
got it,
Okay.
but it wasn't
It wasn't-
exactly what I was
yeah.
looking for.
Okay,
Actually, you know what? The programs are a lot easier to do if you want to do something extra. The programs are really easy, and I can give you the software to do it and everything and help you, but I don't think you need it. Let me look at your grade. Hold on a second.
I think my grade's fine right now. I just did it, so, yeah, I think we're all good.
Okay, I mean, I looked at it. I thought it was, it wasn't what I was looking for the thing. Like, it was in the right paper. Let me see. Let me just look at your grade while I got you on. You're trapped. I should be able to get this up kind of fast. Was it okay before when I did the pre-recorded class? I mean, it doesn't. No one asked any questions. It doesn't seem to make much difference.
Yeah, the pre-recorded classes worked. They went well.
Okay. So I'm thinking like next week I'll do the same thing because I'd like to go to that meeting. I registered for it, but I don't usually go to that one, but it's like cheap and it's a pretty extensive meeting. It's actually the largest science meeting in the world.
Are there any specific sessions that they're hosting that you're interested in attending?
There's a lot of sessions. There's like so many sessions. It's a huge meeting. There's definitely stuff on carbon things, but I didn't actually see that. I only got through Monday, like figuring out what to go to. I think it's 5 days. So, and that took me like 3 or 4 hours to go through all the sessions, on Monday. There's like so many. I don't know. Yeah, it would be good to go to it if you got, so you're just doing grad school now, right? Not working or anything. Like the undergrads are all working, I think, but they don't have time, but basically, yeah, it'd be worth going to it. I think you can still register. Okay, so you're in Kent, that's the wrong one. This thing's slow and zooms running. Wow, this thing's really slow. Okay. So CHE 6034, right?
Yes.
I don't want to click the wrong one. I still haven't graded the quizzes from last week. It's just loading it, so it's taking forever. I wonder if my internet's messed up or something. The class ran okay though. Oh, here, it's got it now. It hasn't filled in the numbers. This thing's like painfully slow. Oh yeah, so you're 90, so you're an A. But plus, what did I say for you guys? Was I just going to give you an extra grade or something? Or no, the undergrads get an extra grade. You guys are straight up. What the grade is, it's just going to be straight grades like A, B, C, no plus minus. So you're 90.5,
Yeah.
so you're like good.
Yeah, I'm good. I just want to make sure that, yeah, that I had sent it, but if
One
it
person
wasn't what you're
got-
looking for, yeah.
You're like second highest. You're like second highest of the group. So everyone's like 89. So that's good enough.
Yeah, I'm
Right
not,
now, right
too
now everyone's
worried.
got an A, yeah.
yeah,
So I don't
okay.
think you need to worry about it. If it comes down to it, I can change the grade after I file it. So if it comes back and I gave you something different, then it's because I didn't remember, and just tell me, oh, I turned in this thing and that's worth something.
Yeah,
And that
okay.
should easily kick you over, I guess. But basically, it wasn't exactly. And usually, like in the past, we did critical reviews. And then it got to be like, basically, it's a lot of work to do it, actually, if you do it right.
Yeah, to do it
So you
properly.
have to find a paper that has something to do with the class, and then you have to go in and like really figure out what they're doing. It's kind of like the quiz, but you have to do it on your own, more or less.
Yeah.
I'll help you. I can help you, but basically it's like the quiz. It's doing that on your own. Like you have to find the paper. That takes a long time. And then
Yeah.
anyway, like the programs are pretty easy. Like the first 3 programs are like simple to do. So in the end, basically people just did programs. But this year,
Yeah.
like I think everyone's going to get an A this year. Like I don't think there's much reason, because it's like it's kind of hard to do virtually. The whole thing's pretty difficult. So
Yeah.
I think it's okay.
Yeah.
So
I think we're all good.
All right. Yeah. So anyway, that's
Thank-
what happened to it. All right.
Thanks.
Gracias.
Good. Or I guess have fun at the conference next week.
All right. Thanks. Yeah.